the number 2 was the idea there that organisms can increase the rate of weathering, but it may not be apparent because they take up the products in their roots. And that glacial outwash is likely to be as similar to a lab setting as you're going to get in the field, because there's very little in the way of that sort of biology going on at the bed of the glacier. So, then number 3, I was trying to get you all to think about, consider the evidence I've given you in these graphs, and eliminate processes based on not so much, idea being partly that you kind of set aside what you kind of know, and rule out stuff based on the evidence provided. So in particular, thermal shock and frost cracking can be ruled out because this is happening in particular in figure 2, under meters and meters and meters of soil in the tropics. So that rules out thermal shock, that rules out frost cracking right out the bat. Part C, honestly, the evidence is a bit weak on that in terms of what I've given you. I'm trying to remember exactly now that I'm standing here in front of all of you what exactly I said in the key on that one. I can't remember exactly what I said, honestly. I can give you essentially the answer is that, okay, here's the answer that I gave. If you're going to have shrink swell action, you need the shrink, and you're unlikely to get stuff dried out to the level at which you're going to have that shrink under meters and meters of soil in the tropics in Sri Lanka. That's at least in terms of the evidence given here in these figures. There are other things, of course, that, if you're going to call on this sort of swell pressure, then you need some kind of tension holding the clay within the pores while it expands. And that's what you get with the reaction-driven fracturing, is you've got that pressure of crystallization, which is actually, it's the pressure of crystallization that's pushing outward, but it's also the tension that is pulling stuff into it, rather than letting that stuff simply squeeze out the cracks. And the same with, we go with frost cracking, but we're not going to get frost cracking in the tropics under meters and meters of soil. So the last one, you go, well, okay, we could do that. Let's see, what would we expect if this is the correct mechanism? Well, we'd expect that in that sort of outer layer, inboard of the first crack, macro crack, if there's crystals filling in the pores, then we would expect to get an increase in the P wave velocity. We'd expect to get a loss in tensile strength, though, due to the micro cracking. And if it's, say, calcite or something like that precipitating in those pores, then we would expect either enrichment or at least not significant loss of calcium and perhaps magnesium in the loss, what you would call it, elemental mass transfer coefficients. And so that in figure 1, you see, okay, yes, in that as yet unfractured brown band on the core stone, there is a peak in the P wave velocity. There's a decline in the tensile strength, so those are both consistent with this mechanism. There's, if we look at calcium on the transfer coefficient, it's at least pretty much stable, or maybe even a little bit above the 0 line. And similarly with the mass transfer coefficient in figure 2 in the core stone in zone 3. There seems to be even a bit of a bump in calcium, although it may not be, it's not necessarily, shouldn't necessarily read too much into that because of the uncertainty of the measurements given by the bars on the graph. But at least it's not showing a distinct deficit or a distinct loss of calcium in that layer. Okay. So, any questions on that before we get to talking about glacial erosion? Let's see, let me just pull out my pictures. I'm going to talk about two different erosion mechanisms in some detail today. Nope.
Like, is there a
Yes.
question? So what size of length are you looking for in response to like the last question on there for each of those?
All I'm looking for really is just enough to, I mean, the last one of all of those, would take the most space because you've actually got evidence that, you know, okay, if I make this, I would, if this is the thing, then I would expect this, and do I see that thing? So, and like I said, I ticked off sort of a few of those, like at least 3 of those that are there. The others, you know, 1 and 2, all you got to say is, you know, this can't happen under several meters of soil in the tropics, so, you know, rule it out. The third one, shrink swell, you know, perhaps it's a little bit more complicated, but still, all you really would need to say is, well, we got to get the shrink before the swell, and it seems unlikely to get that kind of shrink under, you know, again, under several meters of soil in a wet tropical climate. So that's all, you know, and so you're simply going through these things, looking at the evidence presented and going, can I rule this out or not? And for 3 of them, anyway, there seem to be things that allow you to rule them out relatively simply. The other, of course, is a bit, you know, the last one, the one that we sort of think is probably responsible for what's going on. Well, okay, you know, do I see this? Yeah, actually, I do see that. And so each of those things, you know, and this is the way we do science, right? Each of those things that fails to disprove the mechanism gives us a little more confidence that maybe we've got it right.
Do you have to go, like when you were describing the last part of it with the yes answer, do we have to go like super in depth on that one, like saying this calcium level raised to this and whatnot, or?
No, I would simply say, you know, if, and I think I was even relatively specific in the question about calcite, or at least bringing that up as a, yeah, I mean, I mentioned calcite as an example, e.g., you know, there's for calcite precipitation the saturation index of 1.2. So you'd be looking for, okay, do I have the lack of a deficit of those, of things like calcium, and in particular just calcium. So, you know, if this is responsible, then I would not expect to see a loss of calcium in that outer layer, and I don't. And that's, so, like I said, I mean, that particular part of that question would require a bit more detail than the others, because you've got several lines of evidence to consider. Does that answer the question? Okay. All right. Let's then talk about glacial erosion. You know, if I've got my glacier, my rock down here, and I've got this clever guy here. He's kind of chunky because he's ice now. And you know, what's he doing? How's he chipping away at the bed of that glacier? You know, he's under all that ice. It's a little bit, it's a bit tricky, perhaps. He's being a bit sneaky. He's acting out of sight. So what's he doing? Well, as far as we can tell, we've got two major mechanisms. First, we'll talk about abrasion, which is essentially just a fancy word for scraping. We've got quarrying, which is sort of a fancy word for plucking. That is, in this case, we're scraping away at the rock. In this case, we're pulling out chunks, implying that we have to break them as well. So, let's cut to it then, in terms of abrasion. What are the tools for abrasion? Is it literally the ice that's scraping the rock? It's the rocks within the ice, yeah. So, and I'll sometimes call them indenters, because they are making these indentations in the rock. Now, what are the requirements for using this tool and accomplishing this mechanism? Well, let's see. Is deforming ice going to lead to dragging of rocks across the bed? Ice deformation, really? I mean, say we're frozen to the bed?
As it deforms when the rocks move down with the ice that is deforming down towards the bottom.
Yeah, but remember, they're just, I mean, the answer I'm looking for is no. I mean, if the ice is frozen to the bed and it's not moving against that bed, then you're not going to be dragging rocks across it. So that would imply that you need to do some sliding. Now, so we need the ice to be sliding. But what else do we need? We need that the rocks are pushed by the ice into the bedrock. And so that's worth thinking about a bit, because all right, let's consider some facts of life here. Rock is harder than ice. If the base is near the pressure melting point, then any sharp rock will readily be pushed into the ice relatively quickly. So that's not necessarily going to leave it a lot of, I mean, you know, maybe it'll sort of polish if it's fully embedded in the ice, but even if the ice is sliding, that rock's got to be sticking out enough and for long enough and with enough force to actually gouge the rock. And we can, you know, we see the striations. I'll show you a picture. let's see, so that striated rock must somehow be ejected from the base of the glacier and do its work on the bedrock before getting reabsorbed by the ice. So if, you know, if the ice is somehow pulling that grain such that it's digging into the rock, you got to figure that it's also plowing into the ice. And it's probably plowing into the ice faster than it's plowing into the rock. And so, so we need an ejection mechanism of some sort. Either, so, well, what did we learn about when glaciers are sliding and they encounter bumps? What's one way they can get by how do they get by the small bumps? Well, the heat transfer business, the regelation, the sort of Frenchified word for, you know, when you've got the ice encountering a small bump, you know, I might have, let's say, a rock moving along within the ice like that, but at this point, I get melting on the upstream side, up ice side of the bump. And so, at least for a while, that rock is now ejected from the ice because it melted the ice out from it. And so now it's going to get dragged over the bump, perhaps all the way down to here, I don't know. But then I get refreezing over here. So now the rock's going to be reincorporated into the ice stream and continue on its merry way embedded in the ice. So that is, we typically think that abrasion is particularly effective at smearing away the smaller bumps because it has this ready-made mechanism for popping those rocks out of the base and letting them do their work before, and you know, the way I've drawn it, maybe it's wrong. I mean, maybe that rock gets essentially embedded back into the ice relatively quickly. But you know, it's something we could probably actually measure. So the upshot there is that abrasion is most effective on the small bumps that is less than about half a meter, which are the same bumps that regelation, those are the same bumps that the glacier can use regelation to get by. Yeah?
As you have a larger, thicker glacier, could you transfer heat through bigger bumps? Because there would be more pressure and thus more heat?
Not necessarily. I mean, what in terms of the bump size, what matters is, can I get heat back through the rock fast enough to melt the rock, or melt the ice to keep up with the sliding of the glacier. And now, in part, if you have enough of these small bumps, then they will slow down that sliding velocity to whatever can be maintained in terms of getting that heat transfer through the rock here. So there we go on that. Okay. So we've got ice melting, the rocks don't melt, so they get dragged over the bumps. Now, what do we, it's worth considering I mean, you mentioned, Brandon, that you know, would we expect certain things to behave differently under greater thicknesses of ice and so on, where we've got greater pressures and so on. So it's worth considering then, well, what are the dependencies, like what does that rate of abrasion depend on? That is, if I've got some erosion rate from abrasion, well, according to the book, that's going to be equal to, say, the number of rocks per bed area times, say, the cross-sectional area of whatever dent the indentor makes times the indentor velocity. Worth checking that the units work out here. This is number per area, this is area, this is velocity length per time, so it comes out to be a length per time unit on that erosion rate. Yes, we do.
What exactly is the bed area?
Oh, just, this is a concentration, number of rocks per bed area. So, yeah. And in the book, it's sort of first expressed as a concentration, but is it a volume concentration? No, it's number per area, but we've also got this cross-sectional area to account for the size of the rock. Now, this then seems to be something that we should probably try to figure out a bit. So that dent area is, well, it varies. It increases with the drag force on the rock. Rock slash indentor. Want to be careful that we distinguish between the rock that's being carried along by the ice versus the rock that's getting gouged out by that indenting rock. And so what then would the drag force be dependent on? Well, it's going to go with rock diameter bigger rock is going to have a greater drag in that fluid like ice. Remember, we're treating the ice like a fluid. It's going to depend on the ice viscosity. And here's, where, Brandon, we get into issues of, okay, how do different thicknesses of ice affect what's going on? In general, if we've got more pressure, we might be, the ice might be less viscous. And we're also going to multiply by the relative ice velocity. That is, picture this now. If I've got a grain in the ice and the ice is essentially flowing past that grain, it's giving it some drag force with which it's digging into the rock, but how fast that ice is moving past that rock is what I mean by this relative ice velocity. Yeah?
Does the rock diameter, basically assume that the rock is like a circular piece or like a sphere?
Well, imagine a circular cow, right? We just, spherical cow, we don't figure necessarily that the rocks are actually spherical, but you know, that's usually how we draw them if we're just drawing a simple sort of system. Just because that's the, you know, if we make that rock spherical, then it's easy to do the geometric calculations. And then we can at least figure out, okay, you know, there may be, notice I didn't say drag force equal to this product. I said, well, it varies with that, and it's actually going to be proportional to that product. But there's going to be some other factors here, in part having to do with the geometry of the grain. All right, well, let's think about what that implies then. So what do we have? We have that the erosion rate is number of rocks, cross-sectional area, indented velocity. Indented velocity is going to be, you know, say some fraction of the ice velocity. This cross-sectional area of the dent is going to vary with the drag force, which is going to vary with rock diameter, ice viscosity, and relative ice velocity, which again is going to be some fraction of the sliding velocity. And so partly what it comes down to is that our erosion rate is, say, equal to the sliding velocity squared times some function of other stuff. So what other stuff? Including the indenter concentration, the indenter diameter, maybe even the indenter strength, some measure of its hardness or strength. Because it's got to dig into the rock in the bed. Also the bedrock strength. And the ice viscosity. Let's see, did I forget anything? I think that's a pretty reasonable list of things. Now, the thing that we notice here is that I don't have ice weight, ice thickness, anything like that. Why not? Well, there is some effect of its weight, just in the sense that we're not going to get regelation without enough pressure to put that base near the pressure melting point in the first place and lead to regelation being a thing and sliding being a thing. But so, you know, we do need weight for pressure and, let's just say, leading to regelation, but also affecting, for example, the ice viscosity. But the thing to remember here is that all along we've been treating this ice, this solid ice, as if it were a fluid. And given the pace at which these things are occurring, it is effectively a fluid. And so you might imagine, well, what if I pour some syrup on top of a rock and suddenly make it start moving? If that syrup is just sort of maple syrup consistency, then the rock's not likely to do that much. But if it's tar, it's going to take some time for that rock to work its way into the tar. And as long as I'm moving that tar with that rock at the surface, lower surface of it, then it could scrape some rock underneath it if I have enough. If I've got enough force going on to give it enough drag to do so. So it's that viscous fluid aspect that gets us around simply, well, what's the weight of the ice above it? Because that's not really the thing. It's the drag force of that flowing ice on that rock. I think it seems that maybe a picture is in order. Just to, I don't know, maybe you've never seen a picture of striations on rock. You don't believe me, so, here's a picture of some guy on some rock with scratches in it. This is in the Rockies, I believe. I just pulled this off of Flickr, so I don't know this guy. But here we see rock scrapes. And, these are pretty cool. If you didn't know that there was ice there, you'd go, what the hell? Why is that rock all scratched up? Once you know that there was ice there, you know that these are moving in the direction of ice flow. So they give you nice paleo flow indicators. So that's all cool. Let's then move along to talk about quarrying. Again, fancy word for plucking. Sometimes lose track of what I need to turn off and when. Okay.
Real quick question about abrasion.
Yeah.
So I've seen fairly deep glacial striations in the field.
Cool.
Is that a product of just a larger indenter, or is that maybe become a preferred route that other indenters will fall into and move along once they
interesting. I hadn't really thought about your second explanation. That's possible. You could probably, if you looked at sort of the micro topography of the scrape, the striation, you might see whether it looks like there were multiple scraping events or just one. But yeah, in general, if the erosion rate is increasing with indenter diameter, the indenters are, experiencing more drag and making bigger gouges. It's going to take a larger rock longer to get reabsorbed by the ice. It's going to get dragged against the rock harder and longer. There's another twist on abrasion that I'll kind of save for once we've talked about quarrying, though, because here we seem to be saying that we're only going to get abrasion when we've got regelation. But that seems to be actually not quite the case. Quarrying can also be another way to get rocks at the bed of the ice, but unabsorbed as of yet. So let's talk about quarrying. Again, this is simply, we've got to break the rock, and carry it away. The carrying away is not too difficult. I mean, it's ice after all. It's pretty viscous stuff. Yeah.
So, quarrying, is it necessarily that you have to break rock, or can it be like you're actually just picking up, say your glacier is going over a past quarrying or whatever, it's extending past it, and it's picking up pieces of till or whatnot, would that count as quarrying if it's not breaking rock, or does it have to be bedrock that is?
That's a decent, yeah, that's a fine question. I think, at least in my thinking, when we're talking about quarrying, it really implies that we're talking about actually pulling out bedrock. That doesn't mean that glaciers can't entrain stuff from their beds that's not part of the bedrock, but in this particular case, we're talking about, okay, actually, how do you erode bedrock? And it's, you know, it's just a more difficult problem, right? Because you've got to actually break the rock in order to carry it, whereas if it's just loose rock under the bed of the glacier, it's kind of a trivial solution to get it into the ice. Yeah.
So is there like a different term for that and a different like overall process, or just not?
For what she was talking about?
Yeah.
Don't know.
Okay.
Maybe. There's all sorts of fancy terms, you know, in glaciology, so, and I'm not really spiffy with all of them, because I just don't have a head for memorizing terms personally, so. I hear them all, and they kind of go, okay, sounds French, I don't know. And, you know, with quarrying, we get one of those. This is what creates, let me try to say it, roche moutonnaise, or roche moutonnaise. That is lamb's rear or sheep's rear type shapes. Okay, now that we've gone straight there, what are our tools in this case? Well, really, in this case, we're dealing with ice and water, but somehow we've got to create the kinds of stress or pressure gradients in the rock that can lead to cracking of that rock. So I'm just going to put as a tool big pressure gradients. And in terms of requirements, that is, what do I need in order to do quarrying? Well, I have to have sliding again. So now, so far, it seems that glaciers aren't necessarily going to do a lot of any bedrock erosion unless there's basal sliding. Well, we've got to have sliding that produces cavities, or specifically cavitation. So remember, that's what we ended with last time, that if we, you know, especially during spring melt in this big Alaskan glacier, got enough water pressure in there to essentially float the glacier so that it could ramp up over the bumps that were too big to do regelation past and too small to do enhanced creep past. So we need that sliding, we need the cavitation, we need the cavities to drain, or at least partially, or at least some pretty significant pressure fluctuations, but let's just, you know, so maybe we don't need actual drainage, but this is when we get the most extreme pressure gradients, is when they actually drain. And we need that drainage to happen faster than the ice can collapse. So you might recall from last time I was showing you some graphs of the positions of these GPS units that they had on the surface of the glacier over time. And you can see that during sliding they were rising relative to the bed of the glacier. But then once sliding stopped, they were settling back down as the ice deformed and filled in that empty cavity. But of course, in order to do that, you had to depressurize that cavity. So in that case, remember, we had the sliding occurring when the cavity is pressurized, and then cessation of this sliding when the cavity drains, or when the cavities plural in general drain. We suspect that they might not drain all at once, but so let's just consider then this issue of sliding over a medium-sized to large bump in in cartoon form. So got some bump. This down here is rock. This up here is ice, and I've got no cavity because this is prior to sliding. Well, okay, let's move along in time. And again, rock down here, ice up here. And this is during sliding. And so I'm going to create this cavity right here. Now, while the sliding is occurring, this cavity is filled. And pressurized. So, whereas I have ice pressure here, and I've got ice pressure here and here, I have water pressure that is commensurate with the ice pressure that is of similar magnitude to the ice pressure pushing against the walls of that cavity and allowing it to exist and allowing the glacier to skirt over the top of this bump. Now, then what happens later well, at least immediately after sliding, I still have this cavity, poorly drawn, but now this cavity is drained. So now I've got all sorts of pressure from the ice on the rock around the cavity, but within the cavity I have none, just atmospheric pressure. So what then occurs is I get a huge stress gradient or pressure gradient between this point and right next to it here. So if I draw in those contours of stress, it might look something like that. And the fractures in the rock is in general going to crack parallel to those contours of that stress gradient. And that's going to lead to, over time, breaking the chalk and in general sharpening that step on the lee side of the bump. Hence the roche boutonné type shape. Now, that all sounds perhaps plausible. We would like to have some evidence, so let's look at some evidence. As you might imagine, it's not necessarily trivial to look and see what's going on at the bottom of a glacier. So here's this diagram that maybe is better than the ones that I just drew, but same general idea. Here's some illustration based on actual measurements in a fake situation of these stress gradients with varying water pressures in the cavity. So here is an experiment. This was in Norway. They have lots of money to do glacier research in Norway. So they built this whole thing. They've got this concrete fake bump, and they've got some way to pump water in here. In the first case, to pump liquid water in there to melt out a cavity. But then to drain it and see what happens. But listen, not only wait, but listen. So microphones. So this is another, like, let's put in acoustic emission detectors, microphones, to listen for cracking. And specifically they put in 8 so they could triangulate reasonably well to the position. They also cheated a little bit. Well, I'll just show you that. I don't know, I think it's a little bit cheating. They put in a pre-existing crack up here. Kind of wish they hadn't done that because it seems like cheating. I mean, of course you're going to get stress concentrated at the tip of the crack. So, take that for what it's worth anyway. But here's the thing. So if we're watching, these dots are shaded according to the day. So the darker spots are later days in 2004. See, we're only going 0.3 days here, but as I step forward in these slides, we're elapsing time, and this shows a stretch of 2 days in which the cracking events have largely migrated down towards the bottom of that bump, and especially here in the last sort of 0.15 days, we've got lots of acoustic emission events occurring way down here. And sure enough, when they went back in and looked at this piece of concrete that they put in there, there was indeed an incipient crack that formed through there. Let's see. Now, pretty pictures up at the beginning. So, I can be a little oblivious of details of glaciers and whatnot. So real quick, in like the half hour before class, I went and looked back at my pictures that I took in Scotland in September, and just to see, okay, are there any roche moutonnées that I hadn't noticed before? Now that I'm thinking about them, well, yeah, I mean, here and here we see these sort of, somewhat streamlined on the uphill side, but, knocked off to vertical on the downstream side. Now we do see perhaps a bit of rock fall product down here, but this is another interesting point though. So what happens when so we've got this sliding glacier. Eventually the cavity collapses, right? And so whatever's sort of knocked off and lying around, maybe broken rock lying at the base of one of these little cliffs, well, the ice is going to settle back down on it, and then when the ice starts moving again, it's going to carry that stuff off. Hell, it might even keep going during, this cavity might depressurize and repressurize a few times, such that we actually carry some of those rocks along stuck to the bottom of the ice and actually do some abrasion on sort of the Stoss side of the next step. Yeah?
Do these end up forming gremlins?
Ooh. See, I don't know. Drumlins are, I think drumlins are, oh gosh. I wanted to say drumlins might be a depositional feature, but then again, I'm probably wrong about that.
I think they're tilted, so like right over and then it tilts up, and then it's like oblong shape that it creates.
Yeah, I don't think it does. I mean, I thought this was interesting because when I looked on like Google Photos for pictures of roches moutonnées or whatever, typically it's a really big thing. Whereas what we're I thought we were learning was that this essentially would happen especially to medium-sized bumps. So that's why I wanted to go back to my pictures and see, did I accidentally take a picture of any of these things? And it seems that I did. Is there another question over here? Okay. Any other questions in general? Because we're pretty much out of time. All right. Things to be aware of next week. Labs on glaciers next week. Field trip is at the end of next week. And next week we're going to start talking about hill slopes, I believe. Pretty sure. That's what I remember from looking at the syllabus this morning. Yes, Sophia?
Are we going to get a study guide or anything for the midterm?
The study guide is the quizzes.
Okay.
Quizzes compose the study guide. All right. Have a great weekend, everybody. See you on Monday.